All right, welcome to Computer Science 305. This is part 2 of the third part of Java, and we're talking about exception handling. And this next section will be covering throwing exceptions as well as what's called checked exceptions. And so in throwing exceptions, right, it's pretty simple. We have a special type of statement called the throw statement. And so a throw statement is basically you just have the keyword throw followed by an expression, which when evaluated, will return an instance of some exception class, right? So in the way this is worded, it says that most exceptions are thrown automatically by the language system. Well, I don't know if that really is necessarily true. What's actually happening is that within the Java library, which we utilize when we write our own code, everything is a bunch of class files that are being executed, and essentially, with the exception of a few errors, that code actually defines the throw. So it's not that it's being thrown automatically by the language system, it's that the code in the library happens to have throw statements riddled throughout it whenever bad things occur. There's only a few that are actually thrown automatically for you. For example, null pointer exception, stack overflow exception, out of memory error. Actually, any of the errors are thrown automatically by the actual underlying language system. So you have to be aware that it's not that they're thrown automatically necessarily, but more that the code is defined as a part of the library system will throw that. Only a few are thrown automatically by the language system. But anyway, moving forward. So most exceptions are thrown automatically. Sometimes you want to throw your own. In the case that you want to throw your own, you just have to understand what the expression is. It's essentially just throw, and then typically you call a constructor of the new exception object that you want to throw. That's it. When the throw occurs, it will halt the activation record, and it expects that it will be either caught in a try-catch and dealt with, or if that never occurs, will end the system, will kill the program. So we want to create our own exceptions, right? For example, this one called out of gas. So we want to do that. We need to create a new file, just a standard Java file, right? We'll call this out of gas Java, and then it's just defining it to be an extension of a throwable item, right? So typically when we're dealing with exceptions, we want to extend exception. Or you can extend runtime exception. That can also be done. Oftentimes, when you're actually building live code, you really want to be able to define your own exceptions for most classes or operations that you're building. That way, you have this ability to really utilize the Java exception handling system. It also gives you ability to make your code more versatile and easily, I will say, more robust. Anyhow, so if we go back into our test.java class, right, we go ahead and we'll execute. I'm going to just delete all this code. What we'll say is, so we say system.out.print1, and then we'll say try throw new out of gas, and then we'll catch out of gas say system.out.print2, and then we have one last line, system.out.println. Okay, so assuming that this all compiles, we can then again compile the test, and I need to probably compile, go take a look at out of gas because I didn't save it. There we go. Okay, so then we run test, and we see 1, 2, 3, right? So if we look back at our code, it first prints the 1, then it hits the try block and throws the new exception out of gas, and it catches that in the catch block, which then prints 2, and then we print 3. So pretty easy to understand how to do this. You can also, when you define your own exceptions, there's like 5 major constructors you can that you can also use. when you're defining an exception, which can take in a prior throwable that you can pass up with your exception, as well as a message and a few other things. You can also look at the stack trace to see where things happened. Lots of things can be done when you're working with exceptions, right? So using the exception object, the exception that was thrown is available in the catch block. Is that parameter right? So if we look back here, we can see that we have access to the actual thrown exception. We can do stuff with it, right? It can be used to communicate information from the thrower to the catcher. Note that all classes derived from the throwable. They inherit a method called print stack trace, which I'm sure we've all seen. It just prints the stack, right? So the stack of activation records as Java understands it. There's also a string field with a detailed error message, right? That's the get message method that I showed earlier. So essentially we could print that out, right? So we can run this with e.print stack trace. If we run this again after we compile it, we see that it says we had an out of gas exception occurred at test.main line 5, which is this one right here. So it tells us exactly what's happening. If we say the message, right, we didn't actually give it a message. We'd have to handle that in a different way. So in order to do that, we have to, as it shows here, override the base class constructor, which takes in a message. So if we do that, we say public out of gas. And typically in an exception, when you create them, you just create constructors that override, just call the super, unless you have some serious work that you really need to do in there. Most of the time, you don't. So we say just super message. All right, and then if we were to go back in here, instead of printing a stack trace, we say system.out.print line. Maybe we make this a print line. E.get message. And then we can actually throw this out of gas. We can actually give it a message, right? So you have run out of gas. We go ahead and compile and run this, and we see, as we expected, right? We see the actual message occur. So we have to note that the keyword super and constructors, right? Inside of a constructor, you have three choices, right? So if you need to use the super constructor, right, you want to pass in arguments that you took in so that you can make sure fields get initialized properly. You can call super as the first line of your constructor. If you're going to call the super constructor, the base class constructor, it must be the first line. Similarly, you can also call another constructor of the current class by using this, and then in parentheses the values for that other constructor. So let's say, for example, you have multiple constructors, one that assigns all of your fields values from arguments to the or from parameters to that method, to the constructor. Then you can have reduced constructors that send in default values. So then you can just call this the whole time, and then you can call super from the final constructor. So it'd be something similar to this. If I was to actually construct a test. So if I had two fields, right? Let's say string name and let's say string location. Maybe I put some stuff at the end of this. If I was to create one constructor, we'll say which just takes in name, string name, right? And then I have a second constructor which takes in both, because our default location may be, let's just say, home, right? So then we say this.name equals name and this.location equals location. So here we would say, well, we can just call this name and then the string home, right? That would work just fine. But yet again, the base, the call to this or super must be the first line of the constructor. Then you can have whatever you want at the bottom, right? You can have as many other lines of code after that. But the goal here is to reduce duplication, right? Because here I would have to do this.name equals, and then this.home equals, this.location equals home, which is the same thing I'm doing here, just I'm using a default value. So anyway, moving forward. The basic concept of using the super version, which we do in out of gas, is that we need to initialize inherited fields, so fields we may or may not have access to directly. For example, if they're private, so we can't set them ourselves. What we want to do is we want to pass the information that they're going to need up to the super, and that's why we call it the super constructor. So it also should be known that all classes have one constructor, even if one's not included, which is it's the default constructor that takes no arguments at all. Note that if you do define a base class with you actually define the no args constructor, then you must define it in your in any classes that extend it as well. So that just bear that in mind. Let's see. Blah, blah, blah. So then we can also define a new constructor, right? So we have, if we wanted to create, I don't know, say a field, miles, right, for our out of gas. And then we say public out of gas. And then we say string details. And then int m for our miles. Then we can call super details and then set our miles to be m. And then we can actually use this one to use the this. So this details, and then give it, let's say, 5 as the default value. All right, and then we can have a go back to our try block, right? So this code will still work. But now we're just going to say 19 as the miles, right? So then we can say when we catch it, we'll say system.out.getMessage as we said before, and say system.out.println odometer plus e.getMiles. I actually have to create that method really quick. All right, so should work. If we run this, I get one error. Oh, this dot details. So we run test. And we see the same thing, right? We see you have run out of gas, and odometer is at 19. All right, so everything is looking pretty good. So now we move into understanding. So now what do we understand? Well, we understand the concept of the hierarchy underlying exceptions in Java. We understand how to catch exceptions, and we understand how to throw exceptions. So now we have to understand a little bit more underlying how these things work. So now there are two different kinds of exceptions in Java, right? We're not talking about errors. We're talking about exceptions. So we have checked and unchecked exceptions. And what these mean is when you have a checked exception, this is one which you must inform the system that it's going to happen, right? So it must, anytime you call a method that throws a checked exception, that checked exception must be caught, and we must also, the method must state that it throws that exception. When it's an unchecked exception, which the only unchecked exceptions are those which derive from runtime exception, those don't have to be checked. We don't have to, our method is not required to state that it throws that exception, nor are we as programmers required to actually catch those exceptions, right? So these would be any runtime exception-based exception. So, given that, for example, if we were to create a new method. We'll call it Z, right? Say public static void Z, right? And we just say throw new out of gas, right? We'll just copy everything up here. So if we did this, the problem here is that this won't compile, right? Because Z does not declare that it throws this. It doesn't tell anyone what's going on. If we go try to compile, we'll get, we try to compile, it gives us this error, right? It says, unreported exception out of gas must be caught or declared to be thrown. So either we have to handle it right here where we threw it, or we have to state that Z throws this. Why? Because out of gas extends exception. Now, if we were to change this to be runtime exception, right? This would not be the case. So we go ahead and run the, see now it compiles, right? We have no problems anymore. So that's the difference between checked and unchecked. Checked exceptions require us to either handle them or declare where they're thrown that that method throws this, so that it can be then handled by whoever calls that method. So if we take a look here, as I mentioned, errors and runtime exceptions, errors are also unchecked, but they're not exceptions. So you have errors and runtime exceptions are unchecked versus everything else is checked. So just realizing that this is the case is very important, right? And so what happens is a method that can get a checked exception is not permitted to ignore it. That's the basis of this, right? It throws a compile error if you don't catch it. And so anyway, so anytime that you do make a call on a method that throws an exception, that's a checked exception, you must put that call within a try statement with the catch part for that checked exception, right? Or you can declare that you're not going to catch it by claiming that your method will throw it, right? So if we go back to our, we make the change here for back to exception, right? So now we have had this. So we can actually make a declaration on Z here that it throws an out of gas exception, right? So throws out of gas. And so now our code will compile, right? So it compiles, doesn't give us the same error that we had an unreported exception. But now this is going to cause us to have to throw that into a try. So if we just call Z here in main, we're going to get an exception, an error, a compilation error that says that we did not, there's an unreported exception out of gas must be caught declared to be thrown Z on the call for Z. So either main has to declare that it throws an out of gas exception, or we have to actually catch it. And since it's the exact same thing as we're already doing in the try block, we will go ahead and replace that with that piece of code. And we can see that it no longer throws a compiler error, right? So the interesting thing is that so throw clause lists one or more throwable classes separated by commas. So you can declare that you throw more than one thing as long as you separate them with commas. And the basic gist is that it's not guaranteed that your method call will generate that exception, just that it is possible and that you must capture it at some point in time. So and thus must be in some try, right? So if Z declares that it throws out of gas, then Y must catch it or declare it throws too. So if we walk down the activation records, it goes all the way down to the original caller of some method here. So if nothing is capturing it, then F eventually has to capture it. Otherwise, the code will never compile. So in this case, as opposed to when we're looking at runtime exceptions, the code will just compile and we'll just have a problem where it will make the runtime environment crash. So the question becomes why we want to use checked versus unchecked exceptions. Well, so we want to use checked ones, right? Because the throws clause becomes a part of our documentation. We're telling them that we expect something to occur, right, when the method is called. So there's a potential risk to calling this method, and that you have to be sure that you capture this and stop it, and arrest the program in the case that something happened. And the interesting thing here is it's very easy to, the system verifies this, and the compiler insists on ensuring that you handle this exception handling correctly. That's the benefit of this, is that prior to it ever compiling correctly, you will the compiler ensures that you actually handled the exceptions that are likely to occur, right? Thus making your programs easier to read and more likely to be correct, etc. Now, if you want to avoid checked exceptions, you can always define exceptions using a different base class, such as error or runtime exception, right? And then they would become unchecked. So sometimes they're really useful if you don't expect it to be a common occurrence. It's very uncommon, something that we don't normally need to worry about, or it's something that we possibly want to really end. So if we declare something extends error, you can't execute a try catch for an error. So if we make something that's an error, then we expect the program to end. So bear that in mind. This should not be normal operating procedure. So that brings us into error handling. So let's think about this. So error handling is, simply thinking about what are things that cause errors. Well, for example, we could pop an empty stack. That should cause an error. And so we have techniques for this, right? For handling errors, we can verify on preconditions only. There's total definition. There's fatal types of errors. There's error flagging, and then there's using exceptions, right? So this is how do we handle not derivatives of the error class, but just errors in your code alone. And so one of the things that we can do is we can define what are the preconditions for our method to operate, right? And we can use that by validating, either making sure that the user of this method either validates that the preconditions are met prior to calling the method, or we validate inside the method that the conditions are met, and then we continue execution. So for example, if we were in the main method, right, one of our errors that we were concerned with was that args had to have 2 arguments, right, to do the division. Well, we should have been checking that the length of args was at least 2, and that way we could do the division. Otherwise, we just end the program. So that's one way of doing it. The other one was we could allow the exception to occur. We could capture the exception and state what happened. Anyway, so let's say we have some method for working with a stack, right? We can pop the top in from the stack and return it. It should be called only if the stack is not empty. So if we think back to when we were dealing with this, I believe it was in the Java 2 lectures. And so we had stack, and I believe we had remove, right? The remove or pop method. And this is the most generic version, right? So what we're going to look at is we have a node T, we call node n, which is equal to top, and then what we want to do is we want to say we want to look at the link, right, and we're going to get the data. Okay, that's what we're going to do. We're going to get the data and remove the item, right? So we assign top to be the new link, which whatever that might be, but we're returning the data value in top. Well, the problem here is if it's already empty, there's no data to return, and it will cause a null pointer exception to occur. Well, we don't want that. What we want instead is to validate that there's, something that we can actually do. So prior to doing that, in whatever method that we are calling this, wherever we're calling remove from, we want to actually do a check to verify that there actually is something in the stack before we actually call pop. Otherwise, we, I don't know, print an error or something. There's a drawback to this, is that if the caller of the method makes a mistake, right, they didn't actually do the check, then we get the null pointer exception. So, and if it's uncaught, the program crashes. So that's a problem. And furthermore, if you look in the documentation here, this problem is not documented, right? It does not document that this can occur. So the next stage, next thing we could do is we could change the definition of pop so that it always works, right? And so we can define some standard, whatever that means, standard behavior for popping an empty stack, which is similar to like a character by character file IO in C, right? We walk the entire file looking at each character. When we hit an end of file character, then we're done. But the end of file character is the standard way of indicating that the file is that there's nothing left in the file. Furthermore, this is also similar to how the IEEE floating point works. There's nan, so that's non-number, right? And there's signed infinity results. So you can actually have these things that define when you don't have a number, or when you have a number that's too large, or an operation that's too large to represent something. Typically, infinity, like you have a negative infinity or infinity, can represent the results of a division by 0 with floating point numbers. So understanding that, we can this gives us a total definition way of thinking about, but you have to make sure that you document that, and that it is truly a standard way of doing things, something that the programmer should expect. In reality, we don't expect anything. There's no standard thing to expect from popping an empty stack. But we could do it, right? So if n is equal to null, we just return 0. Well, if our values can range between negative infinity and positive infinity, then returning 0 might be a bad thing to do. Right, so that means that we have a drawback here, right? One of the drawbacks is if you made a mistake in your implementation of the stack, you can mask those mistakes by your default behavior, and because everything always works all the time. And if the client's popping all the time, they can actually end up in an infinite loop because it's always returning a value, right? So there's no way or there could be other serious bugs on the client side code that are concealed by the way you implement the stack in this way. Finally, you can create you can just force it to crash, right? So you do nothing, and allow the normal no pointer to occur. You could have some preconditions and then a decisive action, or at least the beautiful thing about this is it does not conceal any problems, right? But it still is not very robust of a solution. We just give them an error and then we kill the program. Well, you popped and then we killed the program. That's not really a great way of doing things. Another way of doing it, the reason that this is not a great way is it's not very object-oriented. We always want an object to handle things for itself, not to the rest of the program, right? So we don't want it to be killing the entire program because one object had a small problem. It's very inflexible, right? Different clients may want to handle the error differently, but it doesn't give them the capability to do that. They could have different choices like terminate, clean up and terminate, repair the error and continue, ignore the error, etc. All these are different viable options, none of which the user got to choose. So that leads us to error flagging, right? So we can, and this is a very old style way of doing things where we create a flag, a value of some sort, that we allow the user to be able to detect, right? Was there an error that occurs? So this would require us to query on the object whether or not there was an error, right? Which is not necessarily a great thing, right? It requires them to literally do that. And so you write that code simply by saying we have to write a check in there in our method, right? That checks if it's null. If it is, then we return set the error flag to be true, and then we return a default value. And then So now this gives us the capability. Before, when we were just returning 0, I stated that, well, that's only good if 0 is never an actual value that we might use. If it is a value that we might use, now when the user sees gets the value from popping, they have to check the value first to see if it's ever 0. If it is 0, then they have to check that the flag is not tripped. If it's been tripped, though, they know that value is not a legible value. In other words, that the stack was empty when they tried to pop. So, right, so then we have to add in all this extra stuff to handle the get error, and then we have to reset the error. There's a lot of extra business in there to do this, right? So now, if we pop 2 integers from the stack, as we do in this divide, we get I and j. And then we have to check if there was an error. If there was, we return. Otherwise, we can do the division, right? So, and then you constantly have to, every time do this, right, you have to constantly call and check the error on the stack. Not really a very viable way of handling it. A much more viable way of handling things is using exceptions, right? So the method that first finds the error throws an exception. So in this case, it would be pop, right? They go to pop. We check if it's empty. If it is, then we throw an exception, right? Don't have to check for that, right? We don't have to deal with any of that. All we have to do is just throw the exception. And now if we make it a checked exception, then the user has to handle that themselves every single time. But we can set it up as a unchecked exception, and then if it occurs, then it occurs. It will leave that choice for them to actually handle it on the user of our code. But we can make it part of the documented behavior of the method, which is the best part, right? So in this case, we can create a new empty stack exception. As I said before, we then in our pop method we check if it's n is equal to null. If it is, we throw a new empty stack. Otherwise, we do what we would normally do. We say n.getLink. We assign that to top, and then we return the actual data value. And then it's on them. So if we made empty stack, so now we could actually say that the divide method will throw an empty stack. In that case, right? And then we'll just let it handle it, and whoever called divide will be the one who has to handle empty stack or whatever on down the line. So the advantage of this obviously are that it gives us good error messages even if it's uncaught. It's a part of the documented interface, a documented part of the interface. Errors are caught right away. They're not masked. Caller need not explicitly check for the error. Error can be ignored or handled flexibly. It gains all the advantages of all the other approaches together as one, and handles all the disadvantages of all the other approaches as well. All right. So that leads us to the next part. I'm going to end here, and we'll start up on part